Welcome to LRB Academy. In this video, I'm also going to take you through one of the decay series that the actinide series undergoes, which is Actinium Decay series, starting from Uranium-235. In this video, we'll write the overall reactions, the number of alpha and beta particles involved, and then the number of steps. Definitely, we'll also look at the number of steps also involved. So let's get started. To start, we have to know the effect of alpha and beta particles on a nuclide. If you have an alpha particle, we know an alpha particle has a mass of 4 and a proton number of 2, and beta 2, 0 and -1. So if we have a nuclide like A to the power, like A having a mass of 24 and a proton number of 5 undergoing alpha decay, at the end of the day we are going to release alpha particle, and the principle is that the masses of at the product side will be equal to the masses at reactant side. Total masses. So this one decay to give us an alpha particle, and then we are going to also get another nuclide here. So to get that nuclide, we just subtract the mass of this the alpha particle from the initial nuclide, which is going to give us 20, and the proton number here from this, which is going to give us 5 minus 2, and that is 3. So now we just based on the atomic number alone or the proton number alone, using the periodic table to identify what element is there. So looking at the periodic table, you can see that lithium is the element with atomic number 3. This is just for illustration sake. So if we have beta particles to the effect, assuming we are going to get beta particles here too, beta particle here too, which is 0, 1. This means at the end of the day, the mass number at the product side should be the same as the mass number at the reactant side, right? So, and same thing will happen to the proton number. This means we are going to get a nuclide here. What mass can we add to 0 to get 24? It's just 24, right? And what mass can we add to -1 to get 5? This is definitely going to be 6. So to know the element here, we just based on the atomic number or the proton number and compare to our periodic table, we are going to find out that it is um, carbon. So that is just a basic hint on alpha and beta particle. So let's go. Decay series or decay chain, because we have a radioactive nuclide here, and this radioactive nuclide, because it is unstable, it will decay to give us another nuclide, and that daughter nuclide called a daughter nuclide, and that daughter nuclide is so unstable. So because it's so unstable, it's also going to decay to give us another daughter nuclide, and that one too, when it is unstable, it also decay to give us another one, up to a point that we are going to get a stable nuclide. Mostly for the actinide series, the kind of decay series that they undergo, they end up out lead nuclide, which is very stable. So let's continue. Um, Now that we know that alpha particles affect masses and proton, and beta particles affect the number of protons too. So looking at this, we have 235. You don't forget your starting material. For the actinium decay series, the starting material is 235, right? So don't forget that. So we have 235 and 231 here. This means we have a decrease in mass by 4, and definitely is going to be alpha decay. So alpha decay. Here 231 and 231, and we have an effect in mass number, and this is beta. We have an effect in proton number, which is beta decay. Because when we look at beta decay, you could see that at the end of the day, the nuclide that we produce, 8 atomic number is going to increase. Looking at this here, we started with 24 and we started with an atomic number of 5, and here to get it the atomic number balance, we got an atomic number here of 6. So this is to tell us that this is the effect of beta particles on a nuclide. So this means here we have 90 and 90 plus 1, so effect of beta particles. So let's continue. We have 231 here and giving us 227 here. So what happened? You will see that we have an effect in mass, which is alpha particle, and from this actinium to thorium here, we have 227, 227, 89, 90 beta particle effect in proton number. Mind you, this is not to say that it is only beta particle that has effect in proton number, but alpha particle too also does the same. So here 227, 223 effect on mass number. So alpha 223 and 219 alpha. You can write your alpha very well. So 219, 215. So what effect is here? Alpha. So 215 to 211. This is also going to be alpha. And 211, 211, 82, 83. So this is a beta decay. And we have 211, 207. This is also alpha decay. 211 to 207. So and now the final one, 207, 207, 81, 82 effect in. So this is a beta decay. So now we can look at our total beta particles involved in the actinium decay series. Mind you, this is a standard thing you also have to know. This is just when we are talking about actinium decay series, this is how it is. And it will start from uranium-235 to 207 generally. 207 lead generally. So let's go. And we're also going to look at how it is Y4N plus 3 series. Let's count how many steps are involved in the actinium decay series. Counting the number of arrows will give us that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 steps, right? Oh, sorry. This is 11. So 11 steps. And how many alpha particles are involved and beta particles too. So looking at alpha particles, we have 1, 2, 3, 4, 5, 6, 7. 7 alpha particles. 7 alpha particles. How many beta particles? 1, 2, 3, 4. 4 beta particles. And 4 beta particles. So now to write the overall reaction, we have to know the total number of beta and alpha particles involved, which we just found out. And then now we know that our starting material is from 235, right? Uranium 235. So uranium 235, 235, uranium 92, giving us, let me use a black, and after our total stable nuclide, which is like 207. So 207A2TB, right? How many alpha particles are involved? So we have 7 alpha particles plus 4 beta particles. So this is the net reaction, the net equation for the actinium decay series. And I told you that because we know the number of alpha particles involved and beta particles involved, and we know the effect of alpha and beta particles, like in terms of mass and proton, what they do. So we can just memorize the alpha, beta, alpha, beta, alpha, beta, alpha, alpha in sequential order. So we know our starting material, which is our starting nuclide, which is 23592. So let me write this. We have AB, and then 3 alpha and AB, AB. So if you know this one is sequential order for actinium decay series, and you also know that as we are starting from uranium 235, 235 uranium with atomic number of 92. Knowing this in order, so you start with uranium and you decay it by alpha, you are done with decay with beta, you are done with the resulting product decay with alpha and beta. Then when you get here, it means you are going to decay this with alpha, or the product that you get. I mean, this is to tell you that alpha decay will repeat itself 3 times, and here to alpha, beta, alpha, beta. So doing that, you get to, at the end of the day, you'll be able to draw this. So for instance, I know that for actinium decay series, to start with alpha. So let's say I have my alpha here, and I know effect of alpha is 4 for masses. The effect of alpha on masses is 4, right? So we have 235. So minus 4 is going to give me 231, right? And then for atomic number, it's going to decrease by 2, which is 90, right? So I don't know this element. I just based on the 90 and look on the periodic table to look at the atomic number or the element with atomic number 90. And look at that, you can see that it's thorium. So we just write your thorium. So at that time you know that this is in your head. So after alpha you go to beta. So this will undergo beta decay, beta minus 1, 0. For beta, the mass will be the same. So we are going to get 231. And for the atomic number, this one is kind of increased by 1. So you go to the periodic table, look out for the element with the atomic number 91. So you are going to get protactinium. So you go in that order. This is for alpha and beta. So you do the same alpha, beta. When you get here, you do 3 times for alpha, here, alpha, beta, alpha, beta. Then at the end of the day, you see that you'll be able to draw this without getting to memorize the various nuclides involved. So just memorizing this. So why is this decay series a 4n plus 3 series? Well, just take the mass of any of the nuclide, either uranium here or thorium here, and divide it by 4. So either 235 by 4 or 231 by 4. If you get a number, exactly a number, then it's going to be a 4n series. If you get a number 0.25, then it's going to be 4n plus 1 series. If you get a number 0.5, it's going to be 4n plus 2 series. Sorry. So 4n plus 2 series. If you get a number 0.75, it's going to be 4n plus 3 series. So dividing 231 or 235 over 4, what do we get? We are going to get um sorry, I should not use this. I should have used our overall. Where is our overall reaction? Yes, this is our overall reaction. So we are going to use our overall. This one was an illustrative example. So we are either going to get 235 over 4, 235 over 4, or 207 over 4, right? So we can either use this or that to determine the kind of decay series the reaction is. So if you use this or this, what matters is the point. Either you are going to get a whole number or point something. That will tell you the kind of decay series. So if you use it, let me say I want to use this 207 over 4, this is going to give me 51.75. And I told you earlier that for 4.75, it is 4n plus 3 series. So that's it for this video. Thank you for watching, and don't forget to check other videos out.